Okay, let's consider another series. In this series, we're going to look at central atoms that are in the third row of the periodic table. So let's start with phosphorus pentachloride. Phosphorus pentachloride. So right away, you can tell that this violates the octet rule because it has 5 bonds around the central atom. And that can only be done if there are 10 electrons. So remember that phosphorus has 5. 1, 2, 3, 4, 5. And then each chlorine that bonds to it comes with 7 electrons. So what that means is that one of those electrons goes into the bond and the other 6 form 3 pairs. So you can put chlorine in every position like this until you have a Lewis dot structure that accounts for all of the electrons. But what kind of geometry would this represent? Well, since there are 5 electron domains, one for each of the bonds, you ask yourself, what is the furthest apart that 5 electron domains can be from each other? And the answer is that it is trigonal bipyramidal. So let's try to look at that with some perspective. So to draw a trigonal bipyramidal, let's start by drawing a line and then drawing 3 lines that form a triangle in a plane. So to see the triangle, I'm going to put in some guidelines here. So you can imagine that if these 3 lines were connected, they would make a triangle. And then if you went ahead and connected them to this top spot here, they might make a triangular pyramid. So now I'm going to erase all these dotted lines because I don't think we need them anymore. This is just to help explain the name of this particular geometry, trigonal bipyramidal. Bi because there are 2 pyramids, one going up and one going down. So we'll call that trigonal bipyramidal. Okay, so phosphorus would be in the middle, and then the chlorines would be on each position. They would be in each position. And you can show the unshared pairs of electrons. If you're asked to draw a Lewis dot structure, it's important to always show the unshared pairs of electrons. And to make the phosphorus a little clearer, I'm just going to erase a little spot in the middle and put the phosphorus. Okay, so this explains the molecular geometry of phosphorus pentachloride. Now to determine the shape of this molecule, we simply remember the rule that if there are no lone pairs, it's the same. So this is both the molecular geometry and it's also the shape. Trigonal bipyramidal. There you go. So keep that in mind. I'm going to erase or switch to another board here. I'm just going to flip it over. And then we're going to look at another molecule. This time we're going to look at sulfur tetrafluoride. So SF4. Tetra means 4. So sulfur tetrafluoride. So again, this sulfur's in the third row. And so we know it is capable of expanded valence, but we only see 4 atoms here, so maybe it fits the octet rule, except we have a problem. Fluorine cannot double bond. Let me say that again. Fluorine cannot double bond. So keeping that in mind, Sulfur has 6 electrons. That's a fact. 1, 2, 3, 4, 5, 6. And we can split apart 4 of those electrons to make the 4 bonds to the fluorine, to the 4 fluorines. So I'll write those in. So here's one of them. And remember, fluorine comes with its own electrons. Here's another fluorine. Here's another one. And here's another one. Okay. And what we're able to see when I draw it like this is that we do have a spot that is occupied by a lone pair. So we count the domains. This counts as a domain. So 1, 2, 3, 4, 5. That tells us this is trigonal bipyramidal molecular geometry. We can see it. We can see the line here. We can see the 2 fluorines going off here. And we can see the spot where a unshared pair of electrons resides. So let's just put in the fluorines. I'm going to have you imagine that the sulfur is in the middle there. This is a little cleaner drawing, and you can see that the molecular geometry of this is trigonal bipyramidal. All right, now let's consider the shape, because this has a different shape. The shape, remember, is a result of the atoms. And so one way to look at this shape is to turn it on its side. Let's draw a line and a little pair of lines there. And let's remember the sulfur is in the middle and the fluorines are on the end of all these lines. And if we look at it from this angle, see, it's just like turning it. So here it was, and here it is. All right. So when we look at it like this, you might understand why it was given the shape was given the name seesaw. Well, you might, if you know what a seesaw is. Remember, a seesaw is that toy that sometimes is in playgrounds, although not so much anymore, probably because too many kids fell off. And they play on it. It goes up and down, up and down. So that's what this shape is called, seesaw. All right, we have one more to look at. And to do that, I'm going to have to erase. So let's remove all of this stuff. And let's take a look at another example in this series. So the next example I have for you is iodine trichloride, ICl3. All right. Why don't you pause the video and give it a try and see if you can't come up with a Lewis dot structure. Okay. Okay. So if you did that and you have an idea, it's time to find out if you were right or not. So one thing to keep in mind is that if an atom has a choice between being on an axial position or being on the trigonal plane, it's actually going to end up on the axial position. And that's because the unshared pairs of electrons, 1, 2, 3, 4, they take up more space. And so they prefer to be on the trigonal plane. Let's remind ourselves what this geometry looks like, because my drawing's getting a little off. So let's draw it just clean like that. And so how did I come up with this? Well, let's count. The iodine has 7 of its own electrons. That's going to be 1, 2, 3 for each chlorine, and then 4, 5, 6, 7 for the 2 unshared pairs. And then each chlorine has 7 electrons. So the 7 electrons of the chlorine include 1 that makes the bond, and then the three pairs. Okay. We can see that the molecular geometry has got to be the trigonal bipyramidal again. But let me remind you of why. The reason why is because there are 5 domains. 1, 2, 3, 1 for each bond, and then 4, 5, 1 for each lone pair. So 5 means trigonal bipyramidal. But what about the shape? Well, again, this shape is best understood if we first kind of erase the positions occupied by the lone pairs. We'll put them back, but we'll put them in this sort of pink color. And then we turn the shape on its side. When you turn it on its side, you can see why it might have the name of T-shape. T-shape. So this molecule with the iodine in the middle and the 3 fluorines is called a T-shaped molecule. And I just want to remind you that the T-shape is dependent upon the bonds, but the lone pairs play a role. It's because the lone pairs are there that these bonds cannot spread out any further. And the bond angles that we're talking about are actually 90 degrees. 90 degrees. Okay? There is another example I can show you. This molecule is unusual in that it's one of the few examples where a noble gas was forced to bond. So this molecule is xenon difluoride. Again, I recommend you pause the video and try to write some kinds of Lewis dot structure for this before we go any further. All right, so here we go. Xenon has how many electrons? It has 8 electrons. And here it needs to make 2 bonds to the fluorine. So we're going to need to use 2 of those electrons like that. So here's the fluorine. Well, let's put this up here. And then here's another fluorine here. And I'm going to erase that for a minute. And then we'll put xenon's electrons in pink. 1, 2. But xenon has 8 electrons. So 3, 4, 5, 6, 7, 8. In other words, it ends up having 3 lone pairs. Let's kind of extend out those pairs so we can kind of see what we're dealing with here. And let me remind you that if we draw this again and put the fluorines in, and then we draw out the lone pairs, we can see that this has 5 electron domains. What are they? Well, we have 1 for each bond, so 1, 2, and then we have 1 for each lone pair, so 3, 4, 5. So 5 electron domains means what molecular geometry? What's that word? I'm waiting. Yep, trigonal bipyramidal. Yay, good. Okay, but what about the shape? Well, again, the lone pairs are not invisible, but when we talk about the shape of the molecule, we kind of look at it without the lone pairs, and what do you see? What I'm looking at is a straight line. And the name of this shape is linear. Linear is the shape. Okay, so there you have it. We're going to stop now.